Calculus BC. We are in the last section that we're going to be covering in Chapter 3, that's 3.9. Look at the top of our notes. It says, I can use linear approximations to estimate functions. And it's really using tangent lines to estimate functions. So let's jump in very quickly in boldface here. Wow, we really want to focus in on what this sentence is saying. The main idea of this section is this: the tangent line to a curve stays close to the graph near the point of tangency. So here's the big idea. You've got a visual. You can even pause the video to real quickly sketch this graph. We've got a function with the xy axis. We've got an x naught right here, and of course there is a point associated with x naught. That's the point x naught comma f of x. But of course what we can do, this whole chapter has been about derivatives. There is a tangent line. There is a tangent line that we can draw right here. And this tangent line, you can see that red line is pretty close to the blue curve as long as we're close to the point of tangency. The point of tangency is the point with x naught. So what we can do is actually move over just a little bit. I'm even going to change it to a different color and say, let's just say that I were looking at the point where x was given. Maybe it's x naught plus something. It's a little bit bigger. If I were to come up here, this point on the tangent line in the red line would be very close to this point on the curve. So the function value would be very close to the tangent line value at x, as long as we are close with our estimate to the point of tangency. As long as where we are estimating is close to an initial point of tangency. You could see the further we'd go away, if I were really to move on out, and we wouldn't be doing that, like if we're going to be coming like even way off to the left here, and if I said, ooh, I want to estimate over here, here's your point on the tangent line, and then maybe down here is your point on the curve. The farther away you move from the point of tangency, and the point of tangency is where the tangent line touches the curve, then you get less accuracy in your estimate. So let's take a look at an example. If I could summarize what's happening very, very, very simply, it's all about tangent lines. So use a linear approximation, use a tangent line to give an estimate of the square root of 122. Now, first of all, we should think about a function. And what function are we actually really looking at? Well, I've got a square root. You might guess that this is the square root of x. And it is. That would be the function that we'd be looking at. Now, of course, we want to get an estimate at 122 when we plug in x equals 122. So if I may, I'm going to real quickly just draw a quick sketch of f of x. F of x, of course, is a sideways parabola. It's going to look something like that. And there will be a point of tangency. There's going to be some point, you can say it's over here, for which we could use a tangent line. I know already I'm supposed to be estimating what's happening at 122, but is there a friendly point on this curve that we could actually utilize? And I think you could see immediately, I know what the square root of 121 is. That would be 121 comma, well, what's the square root of 121? It would be 11. This would be my point of tangency. So a lot of times we might have to first focus in on what a friendly point of tangency is. And then, of course, we're trying to get this estimate that's moving away just a little bit from this friendly x value of 121. We're just a smidge bigger. Well, let's remember what's happening for the equation of a tangent line. We need two things. We need a point. By the way, you've got that point. You've got 121 and you got 11. So that's great. You're also going to need the slope of the tangent line. So we're going to have to do a little bit of work. What's the slope of the tangent line? Well, it's the derivative. So I'm going to say f of x is x to the 1/2. And this is such a famous derivative, it's actually well worth memorizing. The derivative of x to the 1/2, you bring down your 1/2, subtract a 1 here, you'll be at negative 1/2. And my goodness, I think you can see already, this is going to be 1 over a 2. This is going to come down to be x to the 1/2. But that's actually another way you could write x to the 1/2 is to write that as the square root of x. Well, you know what? I'm going to put a little bar here and say, hey, I want to plug in 121. In other words, I'm going to find out what f prime of 121 is. I want to get my tangent line slope at that point of tangency. So that's going to be 1 over 2 radical 121. Square root of 121 is 11. 11 times 2 is 1 over 22. And that's going to be your tangent line slope. So let's come back over here and see my y1 is going to be 11. My tangent line slope is 1 over 22. My x1, this is where my point of tangency is. It's going to be 121. So we have this right here. This would be the equation of that red line. But you see, we want to get an estimate as to what's happening at the square root of 122. So I'm going to let x equal 122. See, I can plug that in right here and we can see what we get. So real quickly, when we do that, we'll find the y value. We'll find the y value on that tangent line. So we're all on that red line right now. 122 minus 121, well, that's just a 1. So I'm going to get 1 over 22 times 1. It's just that. And then I'm going to add an 11. And you'll get 11 and 1 over 22. So we could say, hey, what is the square root of 122? Square root of 122 is about 11 and 1 over 22. Now, could we have changed this answer instead of having a mixed number? Yeah, of course we could. But look, if I may real quickly, what is 11 plus 1 over 22? You can see it's about that, about 11.045. You can say, well, what is the square root? What's the actual? You can see, hey, that's pretty good. It's about 11.045. So please understand what we have just done. We're very close with our estimate location-wise to where our point of tangency is. I guess what I really want to point out is we'd have the point 122 and 11 all over 1 over 22 right here on that tangent line. Obviously, it's not exactly equal to what the function is. That would be, down here. But we're finding a way to estimate functions. And this is a skill that you'll be asked to do time and again, where you'll use a tangent line to get an estimate. Now, first off, I think what many students are thinking, I know I was thinking this when I was a student as well, this could seem a little bit silly because we did a lot of work to get a tangent line equation, and then we could plug in that x value that was close to the point of tangency. But let's be honest, if I wanted to know what the square root of 122 is, I think everybody would just type that into their TI-84 very quickly, and and then you're getting the real value on the function. You're not even getting an estimate. So it begs the question, is this method that we're doing, is it actually of any worth? Is it of any value, of any good? And the answer, of course, is yes. Listen, we don't always know what our function is. We won't be able to plain and simply say, oh, just plug 122 into our function and work it out. And that can sound very, very strange. I'll give you a little bit of a hint. So very often you might be gathering data in a science lab, and you can ask tough questions like, okay, what would happen if we went just a little bit further than this particular data point, which you could think of as a point of tangency. And you'd say, well, I didn't collect data there. I don't know what's happening when x equals 122. Well, you could use calculus and get a very intelligent estimate as to what you believe would be happening. So that leads in, by the way, to where we're going just next. I want to show you that the next problem that we have in the notes is tabular. It's a table problem. And I do want to point out something to you. I think when you're looking at this table, you're going to see that the table is actually all data given the derivative. You can see that. You've got x and then you've got g prime. So this time they're giving you g prime, and then that can happen. So you're getting these rates of change, and perhaps you know these to be true. So they're saying selective values of g prime, the derivative, are given in the table. It's known that g of 7 is 14. Guys, very importantly, as soon as you read g of 7 equals 14, that is a point. It's g of x normally, so whatever's inside those parentheses, that's an x value. You could call that your x1. Here's your 14. We could call that a y1. So I have a point. And wow, I've got all these derivatives. Derivatives, of course, are slopes of tangent lines, aren't they? So they want us to find an approximation of g of 7.2 using the tangent line at x equals 7. At x equals 7. So once again, they're saying, please give me a tangent line. Over and over and over again, we're going to do that. Okay, so we've got point slope form for a line. So we have y minus y1 equals the slope of the tangent, m, times x minus x1. And real quickly, kids are going to say, well, I see what's happening. It's y minus 14 here, and it's going to be x minus 7 here. The 7 comma 14 is the point of tangency. See, that's right here. And in fact, we want the tangent at x equals 7. Dare I say, I want to show you something. Let's just come back here. You know what they're really saying in this problem? They're saying, hey, this point of tangency is when x equals 7. That's what they're telling you. What does that really mean? The tangent line slope is going to be at x equals 7. So they're really trying to confuse you here. Get rid of everything. You see, you want the tangent line slope at the point of tangency, at x equals 7. It's this thing. It's negative 4.1. Wow. And there you go. That would be the slope of your tangent line at x equals 7. Therefore, we have our equation of our tangent line at that point of tangency. And now we're going to let x equal 7.2. And then it becomes number crunching, right? We'll have y minus 14 equals negative 4.1 times 7.2 minus 7. And of course, 7.2 minus 7 is 0.2. So this is negative 4.1 times 0.2. How about we add a 14 over? It's a minus 14. I just add a 14 right there. And this is going to be what we're looking for. we could just get our calculator out real quickly and just type in 14 minus 4.1 times a 0.2. And evidently that's 13.18. But what are you really finding? Look, I don't know what my function is. I don't have an equation where I can just plug it in like a square root issue. Like, hey, plug 7.2 into the square root. Well, no, we don't know what the function is. But, wow, here we are moving forward. We're saying, look, even not knowing the formula for the function, I would expect that that g of 7.2 is close to 13.18. All right, one last one. A little bit shorter video, thank goodness. Here we go again. Just read it through in its entirety. Let f be a function. There's some point on it. The tangent line slope is given. Wow, look at this. An implicit form of a derivative. It not only has x, it has y in it. And the graph of f passes through a point, 2, negative 4. Wow, you know what? That is so critical. You have a point. And we would like to get a linear approximation at x equals 2. This means this point is the point of tangency. This 2, negative 4 is the point where our tangent line is drawn. So we also need the slope, and that comes from the derivative. dy dx is equal to 1/2 x minus 1/2 y squared. But we're going to, look at this, we're going to plug in a 2, negative 4 right here. And that's going to be 1/2 times 2 minus 1/2 of negative 4 squared. And half of 2, well, that's just a 1. Negative 4 squared is positive 16. Half of 16 is 8. So I've got 1 minus 8. I think we all know 1 minus 8 is negative 7. But you know what? You just found the slope of the tangent line at that point of tangency. So we're almost done. I think you're going to see it's a common theme of writing the equation of this tangent line. And then we're going to be able to really get a nice estimate. This y minus negative 4, of course, turns to a y plus 4. But we would like, as we're reading this, get the approximation at for f of 2.3. So you know what? We're going to let x equal 2.3. Then we're virtually done. Let's clean it up. We'll have 2.3 minus 2, and we all know 2.3 minus 2 is 0.3. So we'll have that 0.3 times minus 7. If I bring that 4 over, subtract a 4, you'd have that. You could definitely get negative 4 minus 7 times 0.3. So it wouldn't take you too long to calculate that. Negative 4 minus a 7 times a 0.3. Hit enter and you'll get negative 6.1. Remember, that's what you're seeing on the tangent line when x equals 2.3. We're asked what f of 2.3 might equal. Again, we don't have the actual function to plug that in. Unlike example 1, we can't just say, hey, just plug 2.3 into this formula and work it out. No, we don't know what the function really is. All we know is what its derivative is, and then we're able to get this estimate. Hope this is making sense, and we'll be doing a worksheet together, really spiraled review, a lot of old stuff mixed in with this.